Welcome to Presentation 32. Today's subject is going to be the display touchscreen. Now let's start by looking at the architecture. The touchscreen is part of our layer 3. Now we're going to be using the capability that we learned in layer 3 displays. We're going to be using our UART framework, SPI framework, and IO port framework from layer 2. So let's see the agenda. So today, first I'm going to give you a description of the touch display. We're going to go through some of the schematics. We're going to look at the data sheet for the XPT 2046 sheet. We're going to talk about the communication between the microcontroller and the chip 2046. We're going to go through a first sample program, which is going to be the what I call data collection. Next, we're going to go through sample 2. And finally, we'll go through our summary. So let's start with the description. So a resistive touch screen is built from two thin transparent layers. Each layer has a special coating that can carry electricity. The two layers are separated by tiny spacers so they don't normally touch. So you have two thin layers that are transparent, and here you can see the spacers, the bottom layer, and then this is pasted into the actual TFT display. Now, when you press on the screen, the top layer bends down and makes contact with the bottom layer exactly where you press. And at that spot, the two layers become electrically connected. So they both have a coding that can carry electricity. So when you press on the top, it's going to touch the bottom layer. So they are basically going to be connected. So if I put a voltage on the top layer, then I can measure the bottom layer and I'll see that at the point where I touch, because at the point that I touch, there is a voltage. Let's see how this works. First, the controller puts a small voltage across the bottom layer. So we put a voltage on the bottom layer. The bottom layer has a smooth voltage ramp from left to right. Now this is important point. So we put a voltage here. Now the voltage across this screen is going to be different. It's going to increase or decrease as we go from left to right. Because don't forget that there is this coating, electrically coating, you could say a metal coating, and there is a resistance changes as you touch the coating. So the further you get away from the edge, you're going to have more resistance. So there is that's why they say there is a voltage ramp. The voltage changes as you go from left to right. So no matter where you touch in this screen, the voltage is going to change. Or I should say you'll have a unique voltage every place you touch. When the top layer touches it, the top layer now picks up the exact voltage at that position. So when I touch, you're going to pick up the voltage, a distinct, unique voltage. By measuring that voltage, the controller knows how far across you touch. So as you move, you touch different location, the voltage changes. So you can figure out how far you've gone because of the value of the voltage. Now, we can do the same thing with the other layer, this time putting a voltage from top to bottom. So what I do is now in the bottom layer, I put a voltage in such a way that I can measure from left to right. Now I'm going to put a voltage on the top layer, but this time I want to be the voltage should change when I go from top to bottom. Again, by touching points, transfer the voltage to the other chip. Measuring it tells the controller how far down you press. So I put a voltage here so I could measure the voltage would change from top to bottom. So I touch some place, I'm going to get a unique voltage, and then I can figure out how far I went from how far from the top I've gone. So basically, the idea is that I'm going to get the X and Y coordinate by applying voltage to one or the other layer and measuring those voltages. So now for designing this touch screen, I have two designs options. The first one is resistive touchscreen interfaces directly with the microcontroller. And that's what we did on my presentation one. I took a resistive touchscreen and we hooked it up directly to the controller and made it work. Now the design option two, is what we're going to be doing today. The resistive touchscreen interfaces via the XPT2046 chip with the microcontroller. And what's going to happen is the chip is going to be responsible for managing the resistive touch display, sensing when it has been touched, so forth and so on. And the controller job is going to be to request information from the chip. So let's look at our display and see what we have. So this is the display that we've been using all along, which is the 2.4 TFT SPI 240 by 320 display. And if you look on the bottom of back of the display, I should say, you can see the 2046 touchscreen decoder here. And if you look at the pins, you have a set of pins to deal with the TFT LCD control, and then you have a set of pins to deal with the touch controller. These are as far as the controller is concerned, is dealing with two different SPI interfaces, two different SPI systems. Now this shows you the display from the front, and what I did is I put in the display a couple of boxes, red, blue, yellow, and white, and a couple of lines to make it look nice. And at the end of the day, what we're going to do is we're going to be touching the different buttons, and we're going to figure out how to make them work so they do something. So let's, and again, the controller is the ILI 9341 controller. That's what we've been using all along. So let's talk a little bit about the 2046. So the XPT 2046 is a resistive touchscreen controller chip. Touchscreen controller acts as a bridge between the 4-wire resistive touch panel and your microcontroller. Now the 4-wire resistive touch panel is what we did in presentation 31, made that work. So you need to go back and see this so you can understand what I mean by 4-wire resistive touch panel. Next, real capability of the 2046 is a analog to digital. It has an analog to digital converter, 12 bits of it's a 12 bits that measures the voltage on the touchscreen wire when pressed. So it has a 12-bit resolution. It communicates with the SPI, as I noted. Now, we're talking about the chip, so we need to look at the data sheet for the 2046. This is the data sheet for the touch screen controller used by our display. So what I intend to do is give you highlights of this document so you can go back and get the basic information that you would need to program the display. All the information I use for the programming the display, of course, comes from this document. So the first item I want to show you is the chip and its interfaces. Now we're going to communicate with that chip to the SPI. So the items that we are going to be using are the clock, the chip select, the serial data in, and the serial data out. That's our interface to the chip. And here in this picture, you're going to see how the actual chip is interfacing with the components of the touch screen. Next item I want to show you is in page 15. Now, table 5 has some good information. Now, as we're going to communicate with the chip, sending it a command in which we're going to request the X position value, Y position value, C1 and C2. So one of the parameters that we're going to need to send that request is going to be A0 through A2. So this gives you the value that you need to put for those 3 bits to get the information. So if you want the Y position, then you're going to have to use the 001 for A2, A1, and A0. Now, if you want the X position, then it would be 101. So for the Y position is 001. Now for the Z1 is 011, and for the C2 is 0100. So as I progress in this document, this is going to make more sense. So let's go to the next thing that I'm interested with, which is at page 22. Now this shows you the 8-bit message that we have to send through our SPI interface to get the parameters that we want. So bit 7 is going to be the start bit, which is always 1. Then we have bit 6, 5, and 4 is going to be the values A0, A1, and A2 that I showed you, which with those parameters you're going to be able to request the X value, Y value, Z1, and Z2. Next, you have the mode. The mode is going to be where you want a resolution of 12 bits or 8 bits. And you have a couple of 2 parameters. One is with the power down mode, and the other one the single-ended or differential reference bit. Usually I put those 2 to be 0, and they've been working fairly well. Now let's go to page 24. And now I'm just giving you highlights here. If you need to come back to this document and you can get the details. I'm just trying to just whet your appetite here. So now let's go to page 24. Now this is where I showed you the PD1 and PD2, which were the power down modes. So the values are right there. Now let's go to page 26. Okay, this shows you how this is going to work. So for the 12-bit resolution, which is what we are interested in. So we do the chip select, bring it down. We have our clock, of course, and then we have our data in. So we're going to send a parameter. This is the start bit. Then we have what parameters we want, and so forth and so on. That's the one that I've been just explaining. That's the control bits. So you send the control bit, and after you send the control bit, which is you're going to request, well, you have the resolution. In this case, we're going to use 12 bits. and you're going to request the X, Y, Z1, and Z2. So after you send that command, then you're going to get the values. So the way this works is the first word that you get, the 8 parameters, 1, 2, 3, 4, 5, 6, 7, and 8, are going to the most significant bits of the value. Follow, then you make another request, and you are going to get the other 4 less significant bits. But the 4 less significant bits are going to be part of the 4 most significant bits of your message. So when you get the message, you have to grab the 4 most significant bits. So in other words, so first I get the first 8 bits and grab the whole thing, and then the next thing I do is I get the 4 most significant bits of the next message, and that's going to give me my 12-bit value. So let's continue here. So we have some other, this shows you how you do for the different modes, the 8-bit mode. And then to finalize, what we have here is an example of how you would hook up your chip to a display. So this would be the equivalent to our display, and this is the chip that we're looking at. So with this, I think I've given you a good idea of what you can expect to get on the data sheet for the XPT 2046. And so we can continue with our presentation. Okay, so let me. So this shows you how we're going to hook up the display to the controller. So we have this is the display portion, which we are going to need the clock, the MOSI. Then on the display, of course, we have to decide on the whether we're going to send a data command. Then we have the reset, and then we have what I call the LCD chip select. Now on the chip select, we're going to have the MISO. Then we're going to have the chip select, which is the TCS, which is going to be to select the touch screen. Then we're going to have the clock, and then the MOSI. Now the touch screen and the display, they're going to share the clock and the MOSI. So the clock and the MOSI are shared. Then the data command reset and LCD chip select, those are unique. Now on the touch screen, we have the MISO is unique because we don't get any feedback from the display, so we don't use it, so we don't need it. And then uniques are going to be the chip select. Now the MOSI and the clock are shared. Now the important thing about this thing is that the display is a 3-volt display. So you need to use this 4050 chip to go from the 3 to the 5 and the 5 to the 3. Now in the case of the MOSI, of the MISO, you can go directly because the MISO just goes one way, and the ATMEGA 328 has no problem on reading the 3-volt LCD display MISO. The rest of the signals, they have to go to the 4050. So what you have on the ATMEGA, you're going to have chip select for the display, the reset, data command, MOSI, clock. Then you have another chip select for the touch screen and your MISO. So important, we have 2 chip selects, and we need to handle them very well. Either one is down, they have to be, you have to only one at a time. So now let's look about how the data transfer happens. And this comes out of the data sheet. So we said a command. Now, this is what the command looks like. In A2, A1, A0. Now, that's the information we got from the data sheet. So if you want the X parameter, you have to send a hex D0. If you want the Y parameter, you have to send a hex 90. If you want the Z1, you have to send the hex 80. And if you want the Z2, you have to send the hex C0. So that's the 4 commands that we're going to use to get information from the chip. Now, how does the information come? So we send the command, and then we need to send 2 more commands, dummy reads, to get the data. The first one, we're going to get 8 bits that we're going to use completely. So that'll be 1, 2, 3, 4, 5, 6, 7, 8. So we're going to get bit 4 through 11 of our message. So we're going to use those 8. Then we send another dummy read message, and this time we're going to get 8 bits, but we're only going to use the 4 most significant. So let's see how we do that. So this is the routine that's going to do that. So first we get the command, which is going to be one of these 4 numbers. Then what I do here is I say the chip select for the LCD, I bring it high. That's just for insurance. I want to make sure that everything is okay. So I set this to high, and then I send my chip select for touch. I change it from high to low. Then I send my command, which again is one of these 4. And then I have 2 dummy SPI message to get the data. The first one I call high, and the second one I call low. So I get those 2 parameters, and then I deselect the touch screen, and then I put together the result. I take the first message and shift it 8 to the left, which makes it the 8 most significant bits, and then IR it with the low, the 8 bits of the low. Now I'm only interested in 4 bits of there, so I shift everything to the right, getting rid of these parameters that would go here, and then I send back the results. So that's how we're going to read the touch. Okay, now we need to talk about calibration. The touch controller reports position in raw ADC counts between 0 and 495. That's just the 12-bit resolution. That's in Machiko. Now, here's where it comes a little bit of a complication. The physical glass and the display pixels aren't perfectly aligned. The raw, mean, and max values aren't exactly 0 to 495. So what I'm trying to say is that the display is a 240 by 340, 320, 240 by 320 pixels. So somehow we're going to have to make a 0 to 495. We're going to have to normalize it so it represents a 240 by 320. Not only that, but if you touch your display on the left corner where you would hope that is 0, 0, the display may be 0, 0 on your mind, but the number that you get from the touch screen could be anything, because you don't know what's the resistance at that point, so you need to account for that. So don't forget, you have a touch screen and you have a display, and now you have to make them match. They're independent. So how do we do that? So touch and hold the top left corner, read the X and Y, and store it in the row X minimum and row Y minimum. So basically what I'm saying is you go to the left corner where you would expect to get a 0, 0, and you see what is the touch screen telling you, what are the values of the touch screen at that point. Next, touch and hold the bottom right corner, read the X, Y values, and store this on the row X max and Y row Y max. So if I go to the bottom right corner, I would expect to get the maximum value in the display would be the 240 by 320, but I don't know what's going to be on the touch screen, so I'm going to get those values. Next, we are going to calculate what I call a calibration factor. So what I take is I take the X max and subtract it from the X minimum. And that's going to give me the number that I have. And then what I'm going to do is I'm going to take the screen width and divide it by that. So in our case would be, I would take the 240 and divide it by the number of, I could call it ticks, so I could call it number of units that I get from the resistive. So I can say that the touch controller is going to give me between 0 and 495 units. And now I have to figure out what do they represent when it comes to the display, which is a 240 by 320. So I take the 240 for the X, and then I see how many unit is the whole for the whole width. Then I do the same thing for the Y, but the screen width in this case is going to be the 320. Now, this is how I normalize the input. So the calibrated is going to be the row X. That's what I just read. I'm going to subtract the minimum, and then I'm going to multiply it by calibration factor. Now, I'm going to do the same for the Y. And I'll let you think about this. So instead of trying to explain it and get all confused, I'll let you figure this one out, and you'll see that it makes a lot of sense. Now, note, if touching the top left gives you the bigger row X than bottom right, swap the min and the max, so math still works. So what happens is that sometimes we could say the left corner is going to be the 0,0. Well, it could be that the way the voltage is being placed, that the left corner is the highest voltage. So the ramp goes from left to right instead of going from right to left. So let's see how we do this on the on our code. So first we're going to say, hey, read touch, which is what we just looked at. And that's going to give us the X position. So that's going to give us the X position. Then once we get the X position, then we're going to map it using the calibration to the 240 by 320. Next, we send the read touch, which is the X90, and we get the Y, and then we map Y. Now, what do I mean by mapping Y? So I use these two routines. Now, the row max in our case is 856, the X max, and the X minimum is 247. So I got those numbers by touching the left corner. And when I touched the left corner, I got my X min, which was 247, and I got my Y min, this should say Y min is correct, which was 275. And then I touched my the bottom right to get my X max and Y max, and the X max turned out to be 1856, and the Y max turned out to be 1920. So what I do is as follow. So I have my, to get the X mapping the X. So I get the max X, I subtracted from what I got, my measurement, and then I multiply that by 1856 minus 247, which is this raw max minus raw minimum. And I subtract that divided by 240 and multiplied by the number of units that I got, which is the max minus what I got. Now I do the same thing for the left, which is the max y minus the y that I just obtained, I just read, multiplied by 320 and divided by max y, which is 1920, divided by minus 275, which is the y minimum. So that's the calibration. So at this point, we're ready to go into our sample program 1. So first, we're going to capture the touch input. Write code that continuously check if the screen has been touched. When touch, read the X and Y position. Step 2, collect the sample data. Identify the region of the screen where you want the collection to take place. So basically what I'm going to do is I'm going to move my, I'm going to touch the red square in the stylus the same way I'm doing right now. And then I'm going to go to the next button and I'm going to do the same thing. I'm trying to figure out what are the boundaries between the red and the blue. So when I press the red or the blue any place, I can do something happen. So identify the region of the screen where you want the action to take place. And that would be red square, blue square, yellow square, white square. Touch the region multiple times and record the X and Y value. So I take each of the region, I'm going to touch it. Step 3, define boundaries. From the recorded data, determine the minimum and maximum X and Y value for each of the region. This value defines the box boundary for each button or area. So first I have to do work on displaying whatever I need to do. I have to write the code to get the display to show whatever we want to show on the screen. And we know how to do that because I've already shown you how to program the display. Now, once we've done that, now what we have to figure out is what are going to be the boundaries, meaning that when I need to program in such a way that I know that I want to find out if the red, the blue, the yellow, or the white button has been pressed. So that's the first part of the program, is to get the boundaries. And the second part of the program is going to be to actually do something. So here I have just show you the schematic. And let's go to the how we are going to program this. Before I go into the program, I would like to show you this code, which is for the SPI framework. I had to modify this SPI framework because the display and the touch screen work at different, require different clock dividers. In our case, so I wrote this routine where the inputs is the divider, and if you put a case 2, you get 8 megahertz, a 4 would be 4 megahertz, and 8 would be 2 megahertz, 16, 1 megahertz. And by the way, the touch screen works with 1 megahertz, which would be a 16, and the display works with an 8 megahertz, which would be an input of 2 to this routine. And then you have, of course, for 64, you have 250 kilohertz and so forth and so on. So let's get going with the program. So as usual, I'm first going to give you a high-level view of the program, and then we come back to go through the details. So we have a number of the bytes which are going to be used for chip select LCD low and chip select LCD high is to select the display or deselected. Then the same thing is going to be for the chip select for the T, which is touch low and touch high. And then we'll have a couple of chip selects for the data command, and then chip selects for the reset high and low. So let's get into the routine. So we have initialized the SPI. Then we initialize our ports. And then we have our SPI write. And then we have our TFT send commands, TFT send data, TFT resets, TFT init, and those routines, they are all for the display, which is our TFT display. Next, we have the routine that's some of the graphic, which set the window area. We have one to fill the screen, fill the window area. And then we have our read touch. The only new thing of all of what I've been talking about right now is the read touch. Next, you have a routine that says is touch present. Then we map X. We have one for mapping Y. And then we get to the main routine, which is where we're going to do our drawing of all our squares, and also we're going to be initializing whatever needs to be initialized. Now in the main, all the work is done in the while loop, and that's going to take care of sending the data to the serial interface. So let's go back and look at some of the details. So the SPI init, the only main thing here is to realize is that we're going to have a chip select for the LCD and a chip select for the touch. The rest is just standard. Ports init, again, there is nothing new here. SPI write, that's what we always use to write to the SPI. We put the data in one of the registers, and then we wait until it gets done and we return the result. Next, we have the send command and send data, nothing new there. We can reset the display. Again, there's nothing new here. This initializes the display. And this sets the window area. Again, now we have the fill screen and fill window area. That's all, I would say, vanilla display that we've done during the my display presentation. Now here we get to the read touch, which is different. So what we do is we send a command, and the command to the chip which handles the touch is going to be there to provide the X or the Y variables. So what we do, we go through a whole bunch of, we do the chip select, and I just wanted to make sure that the chip select for the display was high, so it's not active. I am double checking that happens, and then I just go the chip select go from high to low. And now I get the command, and the first thing I do is I send the command to the touch screen chip. And then I have two dummy SPIs to get the data back. Once I get the data back, then I deselect the touch screen, and then I calculate the result, which is basically 12 bits, so I take the first 8 and shift them to the left, and then I place the 8, which are the press the next 8 that I got, and I shift the whole thing 4, which ends up with the the 12 bits that I need. And then I return the result. Now I have some routines here which we haven't used, but I decided I'll just put them here anyhow so you see how they work. And basically that to see whether or not the display has been touched. So we can send the command, which is the B0, to the touch screen, and we send it twice, and it's going to reply with a Z value. Then after sending the bit 0, then we can send the Charlie 0, that's hex C0. We send it twice, and then we get what's called the Z2 value. Next, we can transmit those data to the serial interface, so we know what's the value. And again, I'm not using that, but if for some reason you need to know whether or not the display has been touched, then you would use those parameters, and you would have to calculate what's the delta of C1 minus the delta between C1 and C2, and that would give you whether or not the display got touched. But that's something that you have to actually do it to see what are the numbers that come out. Now I have here the map X. So basically we're going to make sure that the raw parameter, we're going to translate them in parameters that are going to go within the limits, X and Y limits of the display, which in the case of the X is 240 and on the Y is 320. So what I do here is these 1856 are numbers that I've already calculated, which is the max X of the display. So I subtract the data that I got, and then this value 240 divided by 1856 my 247, that's going to give me the ratio that converts the raw value that I have into display. I would say into display numbers, that mean between 240 and 320. Next, I have the map Y, and again I do the same thing. I have to calculate what's the actual value that I got, which is the maximum value minus the actual value, and then I multiply it by this ratio, which is going to give me, it's going to convert this number into a parameter between 0 and 320, basically. And X is doing the same. When I do this operation, the parameter that I get is going to be between 320 and 240. Next, we got to the main routine. So what I'm going to do here is I'm going to need the ports, you need the UART, you need the SPI, and you need the display, the TFT. Then I have my raw X and Y values, and then the actual TFT position once they've been mapped. As usual, I start with the hello touch, and I fill the whole screen with purple. Then these parameters, what they're going to do, they're going to create the white, red, yellow, and let's see, the white, red, blue, and yellow squares. Next, when I get going, I'm going to, when I initialized, I forgot to note this. When I initialized the SPI, I set my clock to 2 parameters. So that would be the 8 megahertz, like I noted. So I start with 8 megahertz. And then when I get, after doing all the displays, I go ahead and set it to 16. So in the display, I don't know if and we'll see it. We have first a straight line, which is white. Then we have the white, red, blue, and yellow squares.
and then we have another little white line that I put, so it looked nicer. So that's what this parameter is doing. And then I set the clock to 1 megahertz. So then we get into the while loop. So the first thing I do is I read the X. Next, I read the Y. So D0 and 90, that gives me the X, that gives me the Y. Then after that, I map the X. So that's going to turn the number to the between 320 and 240, the dimensions of our display. And I do the same thing for the Y. And then I go into the switch. So we have the case 0, and we have in the case 0, we're going to transmit the serial. We're going to transmit the row X and row Y, and then a new line. One thing that I needed to note here is we have the switch is set to 1 to this particular. So in this case, we're going to send the map values for the X and for the Y. And then if the switch would be value 2, then we would send the touch values. So what I'm trying to do here is I have this routine, and before you compile the program, you have to decide what is that you want to do. You want to get the raw data, you want to get the map data, or you want to get the touch. Because this routine, what we're going to do with this routine is get the data so we can figure out what are the boundaries for each of our squares. So let's go to the next one. So in this case, what we said is we're going to set up to 1, and I'm interested on the data, the X and Y data has been mapped. So with that program, what I've done is I basically did step 1, captured the data, and I collected the data. So now what I'm going to do next is I'm going to define the boundaries. From the recorded data, determine the minimum and maximum X and Y values for each region. These values define the box boundary for each button area. So what I did is I went and with going up and down with the stylus and collecting the data. Then I stopped, and then I went up here again. And I collected all the data of doing this. And this is the 2 little white lines that I was talking about. So I did this for the red and blue, and then I started recording for the yellow and white. So I did yellow, and then I got here and did the white to collect the data to figure out what are the boundaries of the squares. Okay, so the data that I obtained, this is for the red and blue. So I went, as you can see, the white values are going to remain fairly, so I did just here, and then I stopped and came here. So the white values are going to stay fairly stable. However, the X values are going to be decremented in this case. So here you have the value. First, let me show you for the Y. So the Y stayed fairly constant between all these. So it's just going basically. So if for the values of Y between 12 and 117, which is here and here and here, if I get one of those 2 values, then I know that somebody pushed the red or the blue. So now what I need to figure out is which one they press. So if it was the red, then I would get a value between 231 and 141 for the X, which is this. Then it dropped, and then it went between 122, which is between 100 and 22 here. Now, if I look at the ones below, then when I start moving here, then it was, so this is between 112 and 117. Now these ones, they have the same shape, but it's between 183 and 304. So if I get these values, then I know I'm dealing with this area. I just don't know which one. So then I can look at the yellow and the white to figure out which is the square we're dealing with. So let's see how I'm going to go about doing that. So this is the one that I showed you. That's what we got with our program from our test case with SW equal to 1. So how am I going to work this? It's in my do loop. So first I'm going to read the X. Then I'm going to map the X. Next I read the Y and I mapped the Y. And then I ask if the is it the Y position, is it greater than 12 or is it less than 117? Then I know I'm within this range, which means that the buttons can be the red or the blue. So then I go, next step is I say, okay, let's find out if it's the red. So is it greater than 141 and less than 232? That would be the red value. If that's true, then I'm going to print on the, I'm going to send to the laptop the value red, so it displays the red. So the exercise here, what I'm going to do is I'm going to touch the red and I'm going to send information to a laptop. So every time I touch the red, it displays the laptop in a, it displays the, in the next term, it's going to display the word red. Now, if this is not true, then I ask, hey, is this is greater than 22 and less than 100? And it's that the case, then it would be the blue color. So I know from the Y that I'm in this this area. But now with the X, I'm going to find out which one it is. So let's continue and see the yellow and white. So this is the data I got from the yellow. So the X increased, then we had a drop and started here. So that's basically here. Then we have the drop and then we continue here. On the other hand, the Y just remains fairly constant. We're just going Y from always the same value, which is 183 to 304. So let's look at the code. So we continue with our while. Now this blank area is supposed to be the area that what we already looked at. So we get to this point and then the question, it says, hey, the Y is between 183 and 304. So 183 and 304, so we know that we are in this area, in this square. So it can be the yellow or the white. So now we have to decide which one it is. So we ask, hey, is the X position greater than 146 and less than 236? If the answer is yes, then we're in the yellow area. We're right here. And the answer is no, then we ask, hey, is it greater than 8 but less than 96? And if the answer is yes, that means we are right in this area. So what I tried to show you is how we went about collecting the data and how we've used the data to set our boundaries for each of the squares. So we can continue with our presentation.
Okay, so let's continue, and we're going to go into a sample 2 program. Before we go to sample 2 program, I would like to, I don't know if I made that very clearly, presentation before the program. The data that I collected, I used the X term, but then I copy and paste the X term into an Excel spreadsheet, and then I use Excel to plot it. So it's fairly simple. And the software that I'm using is just what you find in any computer, just using Excel, copy and paste. So let's look at sample program 2. Output through the serial interface the color of the button being pressed. Use the boundaries defined in sample 1. So what we're going to do in sample 2 is we're going to push the button in many locations of the red button, the blue button, yellow and white. And every time we push a button, we want the X term to show that what button was pressed. And basically the idea is I press the button, I send it to the X term, but I could be doing anything with that. In program, the one in prior presentation, I showed how to turn on LEDs, but I mean, you can do anything you want. But this is just kind of an idea to show that things work correctly. So let's look at that program now.
So first I'm going to give you a high level of the program, and then we'll go back and look at some of the details. So we have in the pound define, we have where we define how to do the chip select, which I already explained, so I'm not going to do it again this time. Now I have a routine to initialize the SPI, initialize ports, write SPI, then send commands to the display, send data to the display, reset the display, initialize the display. Then for putting things on the display, we have we set the window area, we fill the screen, we fill a predetermined window area, and then we have here a routine to read the touch location, which is new here. And then we have another routine to map information for the X value, I should say. Then we have a routine to map the Y information, the Y value. Now here is the main program where we're going to be drawing the squares and doing all the main tasks to identify when the screen has been touched and what area was actually touched. So let's get into the details. So let's start by the SPI init. The only important thing here with respect to the SPI is going to be that we need to have two chip selects. One is going to be for the LCD and the other one is going to be for the touch screen. Next, the initialize ports. We really don't have anything new here per se. The SPI, routine SPI write, nothing new. Then how to send a command to the display is exactly same as we've done, and I explained it in one of my other prior presentations. The send data to displays and reset the display exactly the same as we've done in the past. Then the initialize the displays. This is just an ILI 9341 display that we've initialized before. Then we already know how to set the window area. We know how to fill in the whole screen, or we have a routine to fill in a particular area. Again, that's not everything is same as before. Now here we get to the touch. The touch is different. So what we need to do here, which is of importance, is we need to make sure that we chip select the touch screen, the correct touch screen. And then I also put the chip select for the LCD on high, just to make sure that everything is okay, is set up correctly, even though it should, but this is just a little of extra. Next, we're going to get the command, which is going to be the command to read X or read Y. And once we send that command, then we need to send a couple of SPI write to gather the data. We're going to get the first piece of data that we get is the most significant 8 bits of the X location. And then the second parameter are going to be an 8-bit word, but we're only going to use the 4 more significant bits to complete our 12 byte word. And then we go and do the chip select deselected by going high. So the result is going to be the first word to 8-bit word, and we shifted to the 8 places because they're going to be the most significant. Then we place the least significant bit, but we're only interested in the 4 most significant bits of this second message, so we shift everything 4. So that's going to, so the result is going to have the 12 bytes that we're looking for, 12 bits that we're looking for, I should say, and then we return the result. Now the map, what they do is they're going to normalize the value. So the X value that we get is a particular number, and that can go between 1856 and 247. And what we want is to have a value of X that goes between 0 and 240. So how we accomplish that is we first we take 1856, which is the max value of X, and we subtract the 247, which is the least value that we can get. And then we take the 240, which is the number of pixels, and divide it by this number, and that's going to give us a fraction. If I multiply it by the number of units that I'm gaining, it should give me a value between 0 and 240, which is what I'm looking for. So this is the max X, and all I have to do is what was sent and what is left. That's the number of units that I have to multiply, and that's going to give me a number between 0 and 240. So now let's look at the map Y. Map Y is exactly the same, and by the way, this Y max, and this should really say Y minimum, these are values that I obtained by going to the left upper corner and reading the value, and then going to the left lower corner, and that gave me these two numbers, 1920 and 275, which gives me the max. And then I use these numbers to normalize the value. In this case, it's going to be between the Y between 0 and 320. So let's get into the main program. So what I'm doing here is I'm going to initialize the ports, initialize the UART, initialize the SPI, initialize the display, which is, I call it TFT because it's TFT display. Then I'm going to define the variables YX, YFTP position, and X TFTP position. That's basically a normalized value, which should be same. It should be should match the display pixels. So first thing, I just fill the screen purple. Then I have a little line in top, which I generated here. And then I have my white, red, blue, and yellow square. And then I ended up by putting another little line on the bottom. And then set a new line. Now, before I get into my while loop, the last thing I have to do here is I need to set my clock divider for my SPI to 16, which is going to give a clock of 1 megahertz. And that's what's required by the touch screen, because when I started, I set the, and I should go back because I didn't notice that, I didn't mention it. When I got started on my SPI init, I set the clock to 8 megahertz, which was a value 2 that I already explained before. And then here I bring it to send a value 16, which is going to give me a 1 megahertz clock. So let's get into the while. So the first thing I do is I send the read touch and send the command to read the X position, which is hex D0. So I send it here, and the result that comes back is the value, the raw value, and then I'm going to map the raw value into a display coordinates by map X. Next, I do the same thing with the Y. To get the Y, I have to send the command hex 90. Once I set the command hex 90, this Y value is going to have the raw value for Y, and then I'm going to normalize it and map this value to a TFTP coordinates. Now, once I've done that, now the first thing I'm going to ask, I'm going to say, hey, I'm going to see if it's in the red or blue box. So I take the Y and say, hey, is the value of the normalized value is greater than 12 and less than 117? If this is true, then I know that the it is between the red and they either press the red box or the blue box. So then I go ahead and ask, hey, is the position greater than 141 and less than 232? If that's true, then I know that they pressed the red button, and I'm going to send the display to the laptop, the value red. So what I want to do is when I run the program, I want to see that I press the button red, and I want to see in my laptop that the red has been sent. Now, if this is not true, then I'm going to check to see if the blue was pressed. So if it's greater than 22 and less than 100, then I know the blue was pressed. And I already explained why that is. So if it isn't here, if it isn't between the red and the blue, then it has to be between the yellow and the white. So this should be the y value, and then I check for my x to see what are those values, and either I can decide that it's a yellow box, or I can decide that it was a white box that was pressed according to this. And then if I press either one, then I'll send it to my displays. So let's go and look at the output of this program. So here I press the red, and you can see the red comes up, then I press the blue, and then I press the yellow, and finally I press the white. Now I'm going to be going across to make sure that everything is working, the boundaries are working. So I have yellow, nothing, white. Now I'm going to go across to check the boundaries. Blue, nothing, yellow, then I go red, nothing, and white. So basically what I did is I went ahead and checked the red, stop blue, then yellow, stop white, and then I went across to make sure that everything was, that the boundary was correct. So let me just show you one more time. So we go red, we go blue alone, we go yellow alone, then we go white alone, then we go red, nothing, blue, then we go yellow, nothing, white. We go across, blue, nothing, yellow, red, nothing, white. So this shows you that the boundary have been done correctly, and then whatever you need those buttons to do, to turn on lights, speed up engine, turn on engines, whatever you need those things to do, all you have to do is put a title to those boxes and then press them, and then do the software code to make those things happen. So anyhow, with this, I think we're ready to continue with the presentation. Okay, so we went ahead with the second program, and one thing I would like to mention here is that we had a program 1 that got the boundaries, program 2 where we used the boundaries. Now, in many cases, you can have, yes, one program, and when your program starts, you tell the user, hey, go to the top left corner, go to the bottom right corner, and then you get your boundary layers right there by asking the users, and that's how you mechanize that. So anyhow, we got to the summary, and in this presentation, I gave you a description of the touch screen. We looked at the schematics, how to hook up the display with the touch to the microcontroller. We talked about the XPT2046 chip. We went through the data sheet. We talked about how to communicate with the chip and the display. We went to sample program 1, where we were able to collect the data that we use on sample 2. So I hope you've enjoyed the presentation. Thank you very much for taking the time to be with me, and I hope I see you in the next presentation. Thank you very much.